This is the first video associated with the chemical bonding and nomenclature algorithm. In this video, we are going to cover properties of ionic and covalent compounds, electronegativity and bond polarity, naming and formula writing, as well as polyatomic ions. Let's start by discussing properties of compounds. Ionic compounds contain both a metal and a nonmetal. They have a crystalline structure, which basically means that they have a regular repeating pattern of the ions. So basically, it goes NaCl, NaCl, NaCl. Their smallest piece is a formula unit, which will be important later on in this unit. They are strongly bonded to one another because they are made of positive and negative ions, and opposites attract. They have a fairly rigid structure, so they are very brittle. If you took one piece of salt, it would break pretty easily. And they have high melting points because of these strong forces that hold them together. A good example would be something like table salt. Covalent compounds are only nonmetals. Their smallest piece is a molecule. They are going to share their electrons. Because they can share their electrons, they can be either polar, which means that they have different things around the center, or they can be nonpolar, which means they are the same. We'll talk more about that later. And they have much lower melting points because they are not as strongly attracted to each other as ionic compounds. Some good examples are things like wax or sugar. Let's do a quick study of the difference between ionic or covalent, because one of the important things you're going to need to be able to do for the test on this unit, as well as for the remainder of the semester, is determine if something is ionic or covalent so that you can properly name it or write its formula. Ionics are opposite one another on the periodic table because they are a metal plus a nonmetal. Covalents are usually close together except for H because they are only nonmetals. What I would like you to do now is I would like you to pause the video and attempt to decide which of the compounds over here are ionic or covalent. Now please check your answers. Most of them should have been okay, assuming that you remember that H was a nonmetal, and you should have based on the chart there. I starred 2, the NH4NO3, and the GS2. Technically, this one here is really composed of all nonmetals, but it's made of things called a polyatomic ion, which we'll be discussing a little bit later. So because they are polyatomic ions, that's an ionic compound. And the GS2 is starred because Ge is a semimetal. Semimetals usually are covalent as opposed to ionic. Let's move on. Something else that we need to discuss is electronegativity and bond polarity. I'm going to write the definition for electronegativity now. Electronegativity is a periodic trend, and it is defined as a measure of how strongly an atom is attracted to an electron in a bond. As you can see from the given electronegativity chart, electronegativity is going to increase across the table, and it's going to decrease down the table. We can use this provided chart to determine the bond type that most likely exists between two atoms. You find the difference between their electronegativities, and that tells you what type of bond you have. If the difference is between 0 and 0.4, we have a nonpolar covalent bond. If it's 0.5 to 1.9, it is a polar covalent bond. And if it is 2 or higher, it is ionic. We're going to run through an example and then I'll give you a couple to try. So for example, if we wanted to determine the type of bond that exists between Na and P, we would find P, and we would find Na, find their difference, so 2.1 minus 1, I get 1.1, and I would label this as a polar covalent bond. Please try these next 3 examples, and then we will go over them. Pause the video at this time. Now, check your answers. Li and F have a difference of 3.1, so it's ionic. N and O is 0.4, so it's nonpolar covalent. And C to N is 0.6, and therefore it's polar covalent. On the test, this chart will be provided, but you'll want to know these numbers and what they stand for. Now let's move on and do a quick review of atoms versus ions. Atoms are electrically neutral, and that's because the protons equal the electrons. Ions have a charge, and that's because their protons do not equal their electrons. There are 2 major types of ions that we're going to be discussing. We have a cation, which is things that are positive, and we have anions, which are things that are negative. Cations lose electrons, that's why they're positive. Anions gain electrons, that's why they're negative. Cations are metals, and our anions are our nonmetals. You'll see here that I have provided a periodic table that has some charges across the top. These are common charges for things that form ionic compounds. Group 1A has a +1 charge. Group 2A has a +2 charge. Group 3A is +3. We usually don't label Group 4A, but you can. Group 5A is -3, and then 6A is -2, and 7A is -1. You'll notice that transition metals don't really have normal charges necessarily, except for a few. Silver is always +1, and then zinc and cadmium are always +2. You'll want to memorize these charges so that you'll be able to use them when we name and write ionic formulas. Let's dive a little bit deeper into ionic bonding. Ionic bonding involves the transfer of 1 or more electrons from one atom to another. It's always a positive and a negative ion, as we stated, and it's going to be a metal with a nonmetal. The cations and anions are going to surround each other. They have that electrostatic attraction, which basically is just that opposites attract that we talked about earlier. Okay. And then you can see there in the diagram that the sodium's electron is being transferred to the chlorine. What that does is give sodium a positive charge and the chlorine a negative. When we write an ionic formula, all electrons have to be accounted for. We're going to talk about Lewis dot structures later on, but just kind of follow through for the moment. So calcium has 2 outer shell electrons because it's in group 2. And phosphorus has 5 because it's in group 5A. Calcium is going to give its electrons to the phosphorus, but then there's still an extra electron. So a second calcium comes into play. And then now calcium has an extra electron, so another phosphorus comes into play. And the cycle continues until all electrons are accounted for. The final chemical formula here ends up being Ca3P2. We're going to talk about a much easier way to do that over the next few slides. Let's start by naming our ions. We're going to start with the cations, the positive ones. You're going to want to write the name of the metal. If it's transitional, you're going to indicate its charge with a Roman numeral in parentheses. There's a couple of exceptions. Silver, zinc, and cadmium don't get Roman numerals. And then there are 2 elements that do that are not transitional. So both lead and tin require a Roman numeral. Okay. Let's name these examples and then you'll try some. So Rb is rubidium. It's not transitional, so it doesn't need a Roman numeral. Fe is iron. And because of the positive 3, it's going to be iron 3. And lead, we said, does need a Roman numeral, and that +4 makes this a 4. Please pause the video and try these practice problems. Now check your answers. Some of them, of course, required a Roman numeral, others did not. And down here, you had to use your periodic table or the provided Roman numeral to determine the charge. Anions are a little bit different. For our anions, we're going to change the ending to the element to IDE. So our oxygen changes to oxide. Our fluorine changes to fluoride. And our phosphorus changes to phosphide. Please pause the video and try the practice problems. Once again, check your answers before we move on. Now, we're going to put them all together. The cation, the metal, is always written first. So when we write the name, it's also named first. We're going to add Roman numerals only if necessary. The anion, we said, changes to IDE. So let's go over these examples. Please change this to just P on your PowerPoint. So Na is sodium, Cl is chlorine, so it changes to chloride. Mg is magnesium, and the O changes to oxide. K is potassium, and S is sulfur, so it changes to sulfide. Notice that I did nothing with this 2 here because it does not matter and does not affect the name. Finally, FeP. We know Fe is iron. It's going to need a Roman numeral. And P is phosphide. Phosphorus has a -3 charge. So to figure out the charge of the iron, we use that -3 to assist us. Ionic compounds are neutral. If phosphorus is -3, the iron has to be equal and opposite to that at +3. So the name is iron 3 phosphide. Please try the practice problems. Pause the video now. Please check your answers. Let's discuss the ones that have Roman numerals, and then we'll go over the one with the star. We're going to use the anion, the negative portion, the nonmetal, to figure out the charge of our transition metal. Nitrogen has a -3 charge according to our periodic table. Therefore, chromium has to be +3. So we put a 3 here. Same thing is true with the lead down here. Oxygen is -2, so lead has to counter that at +2. Here, we have a -2 oxygen, but there are 2 of them, so the overall charge is -4. So lead has to be +4. Okay, the other one should have been okay. For scandium, whoops. Let's do that one over here. We know that phosphorus has a -3 charge times 2, so overall it's -6. So our SC has to be +6. However, this time there's not one SC, there are 3, and I need to know the charge of each SC. So I'm going to take that +6 divided by 3 to get +2. Therefore, when I name this, it's scandium. With a 2 phosphide. There are some extra practice worksheets available on the extra practice module on D2L. This concludes this video. We will continue our study in the next video.